Good morning, ladies and gentlemen. My name is Danillo Graziosi, and I'll be presenting our work depth-assisted compression of full parallax light fields. So here you can see examples of full parallax light field displays. And for example, this one on the top left corner, that's our light field display prototype developed at Ostendo. We presented it last year, and we also had 2 presentations on that prototype this Monday at the same conference. And one common factor between our display and all the other displays implementations that we have here is that they have to deal with huge amounts of data. And the common solution to deal with this huge amount of data is to use compression. And then here at this presentation, I'm going to show you what we at Ostendo did to what is our compression framework, and also a comparison between what is being standardized by the MPEG committee. So just a quick idea of what the MPEG committee has been doing in relation to 3D video compression. So they have started standardization of compression methods for 3D video since 2001, and it has been divided into 3 phases. The first phase targets multi-view content, and the result of this first phase was the development of the standard that's being used in Blu-rays, 3D Blu-rays nowadays. And then the second phase targets auto-stereoscopic content, and that in that second phase they introduce the format of video plus depth. And then on the third phase, that targets hundreds of views. So it's for super multi-view displays, integral imaging displays, free viewpoint TV, and that's where we want to do our contribution, right? The call for proposals to be issued by 2016. And then here's just a summary of our compression framework. At the same conference, we already presented part of this framework, and was what we call the compressed rendering that was represented here by the gray blocks. And the idea with compressed rendering is that it's based on the new paradigm of render and compress in one step, which means that we minimize all the redundant data by rendering only a subset of elemental images. But then we needed a step further here, and so we also included the depth-assisted compression, which complements the initial proposal by adding this intra-reference image compression, which are here depicted by the white blocks. And we chose an intra-image compression because we also want a solution that is low latency, and especially suited for displays. So here, let's review just a couple of those blocks. For example, for the visibility test, that's a new algorithm developed to select a subset of elemental images to be rendered, eliminating redundant data at the generation stage. So we basically take the object and consider the object as a thin plate, and then the distance of this thin plate to the screen or to the capturing surface, it's going to determine the distance between the reference images. And the idea here is just to choose the reference images spread apart enough so that their field of view cover the entire object. And then with those minimal sets of images, we are able to render all the other images in between, because all the texture is going to be present on those complementary images, complementary elemental images. And then we render those elemental images, we get the depth and transform it into disparity, and then we use disparity because it can be coded efficiently. And also another important thing for us is that the disparity avoids the division operation at the decoder side, which simplifies the implementation of the decoder. Our next step then is to get those references and still apply another step, another compression step. And we did that because with the visibility test, we try to remove all the redundancy that exists between the elemental images. But still inside the elemental images, there are a lot of elements that are redundant and that we can compress it even further. And for that, we just applied a very well-known compression algorithm. It's very similar to the H.264 video compression. Basically, for the texture, for the color, we apply this lossy compression algorithm, which performs color conversion, block segmentation, integer transform, quantization, and at the end, just a Huffman entropy encoding. For the disparity, we did not go with what usual 3D video compression standards use. They usually apply also lossy compression for their depth maps, but we here are proposing a lossless disparity compression. And the fact that we are using lossless is that we want to preserve as much as possible the geometry information. And by preserving the geometry information, we have also a better quality at the reconstruction side. So the intra-image compression exploits the remaining redundancy inside the elemental image. We can use parallel decoding architecture since all the reference images are independently encoded. And this is especially useful for our systems, low latency systems. So once we get those reference images, we transmit them at the decoder side or at the display side. We decompress those reference images, but then we still need to generate the entire light field. And what do we do to generate the entire light field? With depth, with disparity, and texture, we could just apply a DIBR algorithm, but in our case, we go a step further. Since we are dealing with full parallax light field displays, we apply what we call a multiple reference DIBR, which is a DIBR that uses multiple references. And also the fact that we apply the visibility test beforehand, we have references that are very complementary. So getting just two references like the VSRS does, just left and right, might not be enough. And we might need to get references that come from top, bottom, and that's what we do here. We basically select lots of references. But then to reduce the complexity and to reduce also the memory footprint at the decoding side, we do also a little bit different DIBR. At first, we just perform forward warping, crack filter, and the merge algorithm with the disparity information only. And then once we get the merged disparity information, then we use the texture to synthesize the texture of the target elemental image. So we test our algorithm and compared it with the MPEG algorithms with 4 types of light field, 4 input light fields. We have 2 light fields. It's the Stanford Dragon, so it's a computer-generated image, and it's the Stanford Dragon position far away from the screen at 75 millimeters, and another Stanford Dragon that's positioned at 1 millimeter. So you see the light field is different. And then also to compare with what sequences that MPEG use for their evaluation, we also selected a horizontal parallax only sequence, which is the B sequence. It's also a computer-generated sequence, ground truth depth map, and also a 2D camera array, like a real scene where the depth map is estimated. So it's not a ground truth depth map, it's just an estimated depth map. And then the first thing that we analyze is just the synthesis. So let's see how our DIBR algorithm works. So here, the results that I'm going to present are not the results with compression. It's just synthesis. And the idea is that why didn't we use synthesis before with full parallax light field? And the problem with full parallax light fields is that the elemental images were too low resolution. And then the resolution actually affects the DIBR. But now, we are seeing displays that have even higher pixel resolution, a higher pixel pitch, a smaller pixel size. And then with that, we have a higher resolution of the elemental images, and now it could start to make sense to use the DIBR to reconstruct the light fields. And that's what we're going to show, that with this resolution, we actually have light fields. We can apply our reconstruction, the DIBR reconstruction. And then we're going to compare 2 synthesis techniques. One is the one used by the MPEG group, is the view synthesis reference software. And the other one is our proposed DIBR, is the MR DIBR, the multi-reference DIBR. Another thing that is interesting that we try to find out here is what is the maximum distance between the reference. And so we tried to identify the image subsampling by testing with only every 2 images, every 4 images, every 8 images, and also our proposed adaptive sampling, which comes from the visibility test. So the visibility test is not a regular sampling, it's an adaptive sampling. So here is the result of, on the top is the dragon, far away from the screen. And when the dragon is far away from the screen, that's an ideal situation for the visibility test. We can reduce the number of reference images because we have a lot of correlation between the images. And then here is the result without compression. This is the result with VSRS. And you can see there's a lot of artifacts, and also in the case of the VSRS, we are only limited to left and right views. I had to do kind of a complicated scheme to obtain the synthesis of all the entire light field with VSRS, and then that's still the result that we got with VSRS. And then this is the result that we got with MRDIBR. One thing that I want to point out here is that we do have a low PSNR. Right, so 24 dB is not a good PSNR. But when you compare subjectively those two light fields, they are pretty similar. And so this is also another indication, and that's like discussed in all forums and 3D video compression forums, how PSNR is not an ideal way to analyze the reconstructed light fields, and we need to come up with a different measurement. And then here is our results with the dragon close to the screen. When the dragon is close to the screen, then we have the problem that we cannot subsample as much the images because the elemental images are not as correlated as in the case of the dragon far away from the screen. And then we saw here that delta 4, that is every 4 references, that is kind of like the maximum that we can go, that we still have an acceptable reconstruction. And this is the reconstruction. You see there's still some holes in the image, and the holes, in our case, they typically occur at oblique angles, which is also something interesting to see, is that if you ask somebody, okay, so do you think this is a good reconstruction? Usually the person will only look at the image at certain angles, won't go as oblique, and the viewer is more tolerable to maybe some artifacts like those ones here. And then here we also propose to use the SSIM, which is a structural similarity index, to the reconstructed images. And right now here we are presenting as reconstructed images, we are presenting just an oblique projection of the images, so that's what we call sub-images. It's just getting on the light field all the pixels that are exactly at the same angle. And we actually presented on Monday a simulation software that instead of getting the oblique projections, it actually takes what the user is seeing, so it takes into account the position of the viewer. And that would be something more interesting to evaluate as a measurement for light field reconstruction than just the sub-images. But here, we just use those. So here you can see also in the case for the dragon close to the display, we also are better than the MPEG software. But then the MPEG reconstruction is not applied, it's not suited for those type of light fields. It's suited more for the sequences that they use to test them, right? So let's see how we score with those sequences as well. And then we see here that for horizontal synthesis, we have a pretty similar result to the MPEG, except that we have a couple of holes here because we don't do hole filling. But the results are pretty similar. Then when I try to do synthesis using vertical references or even diagonal reference, then both methods had lots of problems. And those problems actually stem from the fact that the depth map, they were estimated by doing horizontal parallax, stereo matching only, right? They were determined with MPEG software, and then in that case, they're really not appropriate. They have errors, and then that's why those errors can affect both our methods. One, and then let's say, okay, so the depth was a problem. Let's try with a different sequence. So this is with a sequence that has ground truth, right? And then with ground truth, the results are a lot better. And then in our case, since here I'm also evaluating the synthesis with two references with large baseline, I decided to just implement a very simple hole filling procedure, and that was just extending the background. And so in that case, we have we have also a similar quality, but in our case, we are more computationally efficient. And then now let's see the results with the compression. So the results with the compression, we analyze four methods. One is the Simulcast, that is every elemental image is decoded independently, like an iframe. And then in the case of Multicast, we use the MVC, and in that case, we created this very intrinsic structure to do the full parallax encoding. And then on the case of, we also use the 3DV ATM, which is a new 3D video encoder. And then in that case, we apply view subsampling, so we don't transmit those views in gray. And then we transmit the center view. Every 3 views we transmit. The center one is an I view, and the red views are the P views. And then in our case, we also utilize the view subsampling, but we only have I views here. We don't have P or B views. And then this is the case of the Dragon light field, just analyzing Simulcast. That is, I'm sending all the information here. And then in the case where I'm sending all the information, you can see that JMVC is a lot better. That is, there is a lot more to explore there. There's a lot of correlation between the images. And that's kind of like a good point. Like that's the target point that we should strive for, right? To have this type of quality with only this amount of bit rate. The problem with JMVC is all the latency that it has. To decode the whole light field, you have to decode all images, and that could take a long time. And then here it's using view subsampling. And then that's in the case of view subsampling using the MPEG, the 3DV ATM, and using our decoder. And as you can see, our decoder is a lot better. It preserves the 3D structure. It also preserves the motion parallax. And in the case of the MPEG, one of the problems with the MPEG is, first of all, is the synthesis. We've seen before that the synthesis that I use here, I also use the VSRS synthesis. That's a bad synthesis. And then another problem is that the MPEG introduces artifacts in the depth maps. And then the artifacts in the depth maps also influence the reconstruction quality. But still, they have a very low bit rate. And then now let's compare just our approach with JMVC. So as I said before, JMVC, this is kind of like the best approach. We got the highest quality, and we have a reasonable compression, 34:1. And then in our case, just using view subsampling, that is not compressing the references, we get 30 times more compression. We get 900:1. And although the quality is a lot inferior, that is mainly because of a couple of holes that you can see in the image, and only at certain viewing angles, but the structure is well preserved. You see, we still have structure similarity on the 0.9 here. Then when we apply our compression on top of that, we can even achieve even more compression. So now we go from almost 1,000:1 to 4,000:1. And the quality degradation is very small. So we have just a couple of dB. And then if we compare both light fields, they are pretty much the same. And then in the case of, but that's in the case of when the light field is far away, when the image is far away. When the image is closer, then we got a problem here. We can't afford view subsampling, and then in that case, we don't even have any compression. Although we do have high quality, we don't have any compression. And then that's when the advantage of doing compression on the reference images come into place. So for example, if we do not perform any sort of subsampling and just compress the reference images, we go from 0.9 to 8:1. And then we have also similar quality to JMVC, but JMVC still has 64:1. If we allow some degradation, and that's when we use just some subsampling for those fields, and then we can see there are a couple of holes, especially here on certain views of the image, then we get almost double the compression of JMVC. So that's the whole deal here is, okay, where is the best point? Where can we find the best compression with the best quality, right? So to conclude, we have introduced here a couple of following novel concepts. Similar data format as used by MPEG 3D video. So we use texture plus disparity instead of texture plus depth. But the idea here is that we are also compatible with the MPEG is proposing. And so we can have both formats coexisting in the system. We do this adaptive selection of reference views according to the object's position. And then we do the independent compression of reference views because it's more suitable for parallel architectures and low latency decoding. And we are also more computationally efficient to perform compression and decompression. We have results over 1,000 to 1, good preservation of motion parallax, 3D structures, and just as the last slide, I promise. For future work, we propose improvements in our visibility tests. We make the synthesis algorithm more robust to depth errors. We want to improve coding of view-dependent features such as specular reflection and semi-transparencies. We want to study the bit allocation strategies for the proposed algorithm. That is very interesting. And also we want to consider here not only PSNR, but a subjective PSNR that we can obtain from our simulation software. We want to present real-time architectures for the proposed algorithm and evaluate the performance with also more advanced video compression schemes such as the HEVC, the high efficiency video compression. So thank you. I'm sorry I was a little bit over time, but thank you for... And if I can't answer the questions, there's always my email there. You can contact me.